Welcome everyone to today's tutorial. So we're going to talk about concurrency. So let's start with some revision. So in the lecture, we talked about the recoverability of schedules and transactions. And we said that a schedule S is recoverable if for all transactions Ti and Tj that occur in that schedule, where Ti reads some item that was previously written by transaction Tj, it holds that Tj commits before Ti. Okay, so you can read items that were written by the transactions as long as the transaction that has wrote the item is the one that commits earlier. And this is kind of the weakest recoverability condition. Then we learned about cascadeless, and the definition is that every transaction reads only items that were written by already committed transactions. Now, the intuition behind cascadeless is that you don't need to roll back the transaction that reads if the transaction that wrote the item is being aborted, for instance. And finally, the strongest recoverability condition is the strictness. So in that case, a transaction can neither read nor write an item until the last transaction that wrote that item has committed. So we also looked at some locking protocols, and this was the visualization of the basic two-phase locking protocol. So we had this growing phase during which I can acquire locks. Okay, and at some point, you stop acquiring locks and you start releasing the first lock. And from that point onward, you can only release locks. So you can never acquire any other locks. So there's exactly a single growing phase and a single shrinking phase. And then we talked about various variations of basic two-phase locking, in particular conservative two-phase locking. So for this schedule here on the left, for instance, we could come up with this schedule here on the right that corresponds to conservative two-phase locking. So the main idea is that you need to acquire all locks that you're going to use before you start the first operation. Okay, so even though here we're doing only a write of item A in transaction T2, we need to acquire locks for A and B because later on we're also going to acquire a lock on B. And similarly here, transaction T1, we need to acquire a lock on A and B because we're also writing A and B later on. Now, even though the acquiring locks has to be done initially, you can unlock items gradually. Okay, so we can unlock A here because we're done with it, and later on we can unlock B, and so on. The nice thing about conservative two-phase locking is that it avoids deadlock, but it kind of limits the amount of concurrency that you can get. So in practice, people are using strict two-phase locking. So we can think of this as having just a single growing phase, and then only after you commit, you release all your locks. All right, so now I'll give you some time to work on today's exercises until, let's say, 12:25. Then we'll go through the solutions. Meanwhile, if you have any questions, just text me in the chat. All right, so let's get started. So in this first question here, we're given 3 transactions, and we would like to use strict two-phase locking to schedule the operations. So we want to insert the appropriate lock statements. So let me write this down here. Okay, so initially TB wants to write X, so we need to acquire a write lock on X. So I'm going to abbreviate this as WL of X, and then TB can write X, and the next step, TA wants to read Y, so we need a read lock on Y, and then we can read Y. And the next step, TB is going to read Z, so it needs a write lock, a read lock on Z. And then TC needs a read lock because it wants to read X. Any problems here? Acquiring this read lock? Is this possible? What do you think? Exactly. So, well, actually, TA doesn't have a lock on X, right? But TB already has a write lock on X. And now if some transaction holds a write lock on X, then no other transaction can have any lock on X. So this means that this operation here will be blocked. Okay. And the next step, TB wants to acquire a write lock on Y. But unfortunately, TA already holds a read lock on Y. So this will also be blocked. Then TA wants to execute this write here, so it needs a write lock on X. And of course, this is also blocked because TB still holds this write lock. And note that we can't unlock any of these locks here that we are holding until we commit, because we want to ensure that this is a strict two-phase locking schedule. Okay, and what happens next? Are we going to execute any other operation here? Well, it's actually a deadlock, right? Why is it a deadlock? Well, because each transaction here is blocked. So nobody can make a move. So therefore, we get a deadlock. Okay. All right, let's move on to the second question. So we have 2 transactions, T1 and T2, and we want to first add lock and unlock operations such that conservative two-phase locking is satisfied. Okay, so let me see how we can do this. So we have T1 and T2. Okay, so T1 wants to read A here. So what kind of lock do I acquire for this? Yeah, not quite, because what are we doing here? Well, we want to satisfy conservative two-phase locking. So what was the definition of conservative two-phase locking? It says that we need to acquire all locks in advance. So therefore, we need to look at the entire transaction, all the operations that T1 performs, and check what kind of locks do we need. And we can see, oh, later on, we are doing a write of A here. So we need also a write lock. Okay, so since I need a read lock and a write lock, I might as well just acquire a write lock, because the write lock is exclusive anyway. So T1 will need to acquire a write lock on A before it can do this read here. All right. And then T2 gets to do an operation, so it needs to read A. So again, later on, it needs to write A2. So since we're doing conservative two-phase locking, it will need to acquire all locks in advance. Therefore, it needs to acquire a write lock on A. But now we have a problem, right? Because T1 already holds a write lock. So T2 can't acquire a write lock, and therefore, oops, what's going on here? Therefore, it's blocked. So back to T1. Now T1 gets to write A. And then we're done. So we're going to unlock. So that's what UL stands for. So I'm going to unlock the write lock on A. And now T2 gets its turn. So now this write lock operation here becomes unblocked, because no other transaction is holding a lock. And it can finally execute its read of A, and then its write of A. And finally, it can unlock its lock on A. And that's it. So note that we omitted the commits here. Since they're not in the original schedule, we also don't need to worry about them here. Any questions about this? All right, let's move on to part 2. Now we're going to do the exact same thing, but with strict two-phase locking. Okay. So what kind of lock am I going to acquire for this read here? A read lock, exactly. Because now in strict two-phase locking, we can acquire the locks gradually over time as we need them. And then we get to read A. Then T2 gets to read A, so it needs to acquire a read lock. And what's going to happen here? Can we acquire this read lock? Or are we going to be blocked? Yeah, so we're not going to be blocked. Why? Well, a read lock is a shared lock. So as many transactions as you like can hold a read lock on the same item, as long as no transaction holds a write lock. Okay, so this write lock operation here won't block. So therefore, T2 can also read A. And now T1 wants to write A, so it will need to acquire a write lock, or more specifically, it's going to upgrade its read lock here that it acquired to a write lock. Okay, and is that a problem? Is T1 going to be blocked? It is going to be blocked. And the reason for that is that T2 holds a read lock, right? Now, the definition of a write lock was that it's an exclusive lock, meaning that if you want to acquire a write lock on some item, then no other transaction at that point in time can hold any kind of locking. Okay, and this is not true because T2 holds a read lock on A, so this write lock operation here will be blocked. And the last operation here is the one by T2. So it also wants to write A. So it needs to also upgrade its read lock to a write lock. And is that going to work? Is it going to get blocked? Well, it can acquire a write lock only if no other transaction currently holds any kind of lock on A. But actually, we did acquire a read lock up here in transaction T1, right? And we haven't released this read lock anywhere. So therefore, I can't acquire a write lock here. So T2 will also be blocked. And therefore, we have a deadlock because all the transactions are now blocked. So you can see when you do strict two-phase locking, it's very easy to run into deadlocks. But this is not such a problem in practice because there are some protocols that can break up deadlocks, as we'll see in the next lecture. And now the final question here is that we have been asked which one we would prefer. So this shouldn't be a very difficult question because obviously we want to prefer the schedule that doesn't lead to a deadlock. So we're definitely going to choose conservative two-phase locking. All right. Also, in general, you want to use conservative two-phase locking if the transactions are short, because there's not much that you lose in terms of having less concurrency if they're short transactions. Okay, let's move on to the third question. So now we're looking at the recoverability of transactions, or rather schedules. So now we have these three schedules here, and we want to see whether they're recoverable or cascadeless or strict, or neither of them. So let's start with schedule A. And I'm going to first write down the schedule here so we see what's going on. Note that the C2 stands for the commit of transaction 2 and C1 stands for the commit of transaction T1. All right, so let's start. So is the schedule here recoverable? Yeah, it's actually not recoverable. Okay, and the reason why it's not recoverable is that we have this write here in transaction T1, and later on we have this read here in transaction T2. And the problem here is that it's fine to read an item in transaction T2 that was previously written in transaction T1. But if we do so, then it needs to hold that transaction T1 commits before transaction T2. And actually, this is not the case, right? Because T2 commits before transaction T1. Okay, so this is not non-recoverable. And just to remind you why this is a good definition to have recoverability. So what can happen here is that at this point here, transaction T2 commits and writes its changes permanently to the database, and it has read this value of X, okay, which was previously written in this transaction T1. And then after this commit here, it can happen that there's some error over here. So this transaction crashes or is aborted for some reason. So it doesn't commit. And in that case, we know that all these operations that this transaction has performed are going to be rolled back, right? So none of them have now happened. But this is a problem because we already committed this transaction T2 to the database. And in that transaction T2, we assumed that this value of X was the one that was written in this transaction T1. So you can very easily see that this might lead to some inconsistencies in your database if you allow such a non-recoverable schedule. Okay, so let's move on to part B. Again, I'm going to first visualize the two transactions to make it easier for us to see what's happening here. Okay, so now let's see. So is this schedule recoverable? Well, again, we need to check all the read-write pairs that we have here. And in fact, this is the only write followed by a read of the same item between two transactions in our schedule. So we know that it is recoverable if the writing transaction commits before the reading transaction. And this is actually the case, right? So T1 commits before T2. And now we don't have a problem. So the scenario that I just described on the left, that won't occur here, because what can happen? Well, if T1 crashes before it commits, then, well, all these operations will be unrolled, so they are gonna be undone. And we can simply also abort T2, right? We're gonna roll back T2 just the same way, because we also haven't committed T2 yet. So nothing has happened, so it's fine. And if there's a crash after the commit, right? So after this commit here, well, the transaction is already done. It has already written its changes to the database, so we don't really care whether it crashes after it has just committed. Okay. So therefore, this schedule here is recoverable. Now let's see what kind of recoverability condition it satisfies. So recoverability, so just being recoverable is the weakest one. So let's check if it's also cascadeless. So is it cascadeless? And remember that cascadeless means that every transaction reads only items that were written by committed transactions. So it's actually not cascadeless, right? Because T2 reads X that was written by T1, and T1 hasn't committed yet. Okay, so it's not cascadeless. So why do we care about cascadelessness? Well, if T1 fails at some point before it commits, right, then we also need to roll back T2. Okay, because T2 has read something that T1 has written. And in fact, in the lecture, we saw this example where you have multiple transactions that all read this item X here, and they all need to be rolled back. So you can have a cascade of such rollbacks. Okay, so it's so it is recoverable, but it's not cascadeless, and therefore it's obviously also not strict. So let's look at the final schedule here. So again, let me visualize it first. All right. So what about this one? Is it recoverable? Again, we need to look at all the read-write pairs. So we only have this read-write pair here. Okay, and clearly the writing transaction commits before the reading one. So this is fine. So it's definitely recoverable. Now let's move on. Let's see if it's also cascadeless. So is it cascadeless? Do we only read items that were written by already committed transactions? Well, how many reads do we have here? We only have 2, so it's easy. So this read up here reads X, and X wasn't even written by anyone, so that is trivially true. And what about this read here? Well, it reads X, and when was X written the last time? Well, it was written here by this other transaction, okay? And but this other transaction, T1, has already committed. Okay, so this is fine. So it satisfies the definition of cascadeless. All right, so let's move on. Let's see if it's also strict. Okay, so remember that a schedule is strict if a transaction neither reads nor writes an item until the last transaction that wrote that item has committed. And is it strict? Well, actually, it's not strict, right? Because we have this write here of X. And previously, we also wrote X over here in transaction T1. And at this point here, T1 hasn't yet committed. Okay, so this is not a strict schedule. Okay, so therefore, the strongest recoverability condition that this satisfies is cascadeless. And the final question here asks whether we can change this schedule to be a strict schedule. Well, we kind of already answered that, right? Because we said that there's a problem with these 2 writes here. So we shouldn't be writing something that was previously written by transaction that hasn't yet committed. So this already gives us the answer. So what we need to do is we just need to move this write here to occur after C1. Okay, so down here at some point. So then it becomes a strict schedule if we do that. Okay, so this brings us to the end of today's tutorial, and in fact, of all the tutorials in this course. It is Tuesday, the 20th of April, 2021. And somehow my Google Assistant understood that I was asking for the date today. So it just told me the date. Oh well. So are there any questions? Otherwise, I will still see you in the lecture on Thursday. Remember that there's still the TLQ for you to fill out in case you haven't done so yet, the teaching and learning questionnaire. That's always good to have. And yeah, otherwise, have a good day.